Hi everyone, welcome to Booster Chemistry. Previously we had discussed GOC. Uh, Today we will discuss aromaticity. It is a very small but important topic from exam point of view. Let us start. Aromaticity is broadly classified in 5 types: aromatic compound, homoaromatic, then quasi-aromatic, then anti-aromatic and non-aromatic compound. We'll go one by one. First one is aromatic compound. There is certain condition for a compound to be aromatic. First one is cyclic. It must be closed ring structure. Second one is it must be flat or planar, that is sp2 hybridized or sp hybridized. Complete conjugation of electron means complete delocalization of pi electron. Conjugation means alternate single and double bonds are present in the system. Last one is it must follow Hockel's rule of aromaticity, that is it must contain 4n plus 2 pi electron where n can be 0, 1, 2 onwards. They have certain characteristics like they are highly stable because they have bonding orbital which is completely filled. Here is the example of benzene. Benzene has 6 pi electron in bonding molecular orbital which is completely filled. We will study it in quantum chemistry. Next one is they readily undergo electrophilic substitution reaction. Electrophilic because due to availability of pi electron density both above and below the ring, substitution but not addition reaction, because if they undergo addition reaction they will lose their aromaticity. Since aromatic compounds are highly stable, they prefer substitution over addition. Here is certain examples of aromatic compound. First one is benzene. First it is cyclic, yes, then it is flat or planar, that is all carbon atoms. Here it is sp2 hybridized. Next one is complete conjugation of pi electron. Since here is 3 pi electron, 3 pi bond, that means 6 pi electron, so it follows Hockel's rule where n equal to 1. Next one is cyclopropenium cation. It is also cyclic. It is planar because all carbon atoms here is also sp2 hybridized. Complete conjugation of electron. Next one is Hockel's rule. It also contain 1 pi bond, that is 2 pi electron, that means n equal to 0, so it is also aromatic. Next one is cyclopenta anion, cyclopentadiene anion. Here it is cyclic, flat, that means all carbon atoms is sp2 hybridized. Here is also complete delocalization of pi electron. Next one is it contains 2 pi bond, 1 negative charge. 1 negative charge contains 2 electron, that means total is 6 pi electron, which is followed by Hockel's rule, so n equal to 1. Here is cycloheptatriene cation. It is cyclic, it is planar because all carbon atoms are sp2 hybridized. Here is also complete delocalization of pi electron. Next one, it contains 3 pi bond, that means 6 pi electron, that is it followed Hockel's rule, so it is also aromatic. Last one is pyridine. Pyridine is cyclic, it is planar because all the atoms here is sp2 hybridized. Here is complete delocalization of pi electron. Here the lone pair available of nitrogen atom is not counted during conjugation because it is present in the p orbital which is perpendicular to the sp2 hybridized orbital. It contains 3 pi bond, that means 6 pi electron, so it also follows Hockel's rule, therefore it is also aromatic. Next one is homoaromatic. It is same as aromatic, but there is a difference, that is the conjugated system formed by bypassing one saturated atom. Saturated means that atom is bonded to through sigma bond only. Here is the carbon atom that is saturated, so it has sp3 hybridization. It is cyclic, it is flat or planar, that means all are sp2 hybridized except this carbon. There is also complete delocalization of pi electron over the system. It follows Hockel's rule, that is contain 4n plus 2 pi where n equal to 1, that is 6 pi electron. So it is same as it is same as aromatic compound, but it must be passed by an sp3 hybridized atom or saturated atom. Next one is quasi-aromatic. Quasi means not complete. So it arises due to polarity difference between the system by polarity difference, both the system must gain the aromaticity. Since there is polarity difference, it also has high dipole moment. Here is the example. If we break this double bond, the 5-membered ring will get negative charge and the 7-membered ring will get positive charge. So by gaining negative charge, the 5-membered ring becomes aromatic because it is cyclic. All the carbon are sp2 hybridized. There is complete delocalization of pi electron. Also, it contains 6 pi electron, which is Huckel's rule. Similarly, for 7-membered ring, it is cyclic. All the carbon atoms are sp2 hybridized. There is also delocalization of pi electron. It contains 6 pi electron. So follows Huckel's rule. So both the rings are aromatic. The overall compound is aromatic. Since there is charge difference due to polarity, so we call it quasi-aromatic. Similarly, here due to high electronegativity of oxygen, the carbon, we break this double bond. So oxygen get partial negative charge, carbon get partial positive charge. So this cyclopropenium ring is positively charged. Here all carbon are sp2 hybridized. Complete delocalization of pi electron. It contains 1 pi bond, that is 2 pi electron, which is Huckel's rule. So it is also aromatic. This is arginine. It is a combination of both 5 and 7-membered ring. By breaking this double bond, the 5-membered ring get negative charge and the 7-membered ring get positive charge. So both are aromatic. So arginine is overall a quasi-aromatic compound. Next one is anti-aromatic compound. For anti-aromatic compound, it must be cyclic, it must be flat or planar, that is sp2 or sp hybridized atoms are present in the system. Next one is conjugation. Conjugation means there is complete delocalization of pi electron, but it must contain 4n pi electron, 4n pi electron, where n equal to 1. N stands from 1 to 3 onwards. So here is the example. This is cyclobutadiene. It is cyclic. All carbon atoms are sp2 hybridized. There is complete delocalization of pi electron, but it contains 4 pi electron, which is not followed by Huckel's rule. Similarly, here cyclopropene anion. It is cyclic. All carbon atoms are sp2 hybridized. There is complete delocalization of pi electron. It contains 4 pi electron. Similarly, cyclopentadiene carbation. Here is cyclic. All carbon atoms are sp2 hybridized. There is also complete delocalization of pi electron. It contains 4 pi electron. That means it is anti-aromatic. Similarly, here this compound is cyclic. All carbon atoms are sp2 hybridized. There is complete delocalization of pi electron. It contains 1, 2, 3, 4. 4 pi bond. That means 8 pi electron. The lone pair, since there is 2 lone pair over oxygen, one is involved in delocalization, so one is counted. 2, 3, 4, 5, 6, 7, 8. There is total 8 pi electron. So it is anti-aromatic. Next one is non-aromatic compound. For a compound to be non-aromatic, it must be cyclic, but it is not planar. No conjugation. Don't follow Huckel's rule. Here is the example: cyclooctatetraene. Here it is cyclic, planar because all carbon atoms are sp2 hybridized, but experimentally it does not exist in this form due to high angle strain, so it gets converted into top shaped. Because of top shaped, it becomes non-planar, so non-aromatic compound. Next one is cycloheptatriene anion. Here is also the same case. Due to non-planarity, it is non-aromatic compound. Suppose here is the compound. It does not exist because it is not an aromatic compound. Due to repulsion between these two hydrogen, the system becomes non-planar. Due to non-planarity, it becomes non-aromatic. To make it aromatic, we have to do 2 things. First one is cyclization. By doing cyclization, it gets converted to aromatic compound, or by doing bridging compound. By converting it to a bridge, we also get an aromatic compound. Next, for polycyclic non-benzoid system. Benzoid means benzene-like, non-benzoid means not benzene. So there is a rule called Craig's rule. For non-benzoid system, we have to see if the system is cyclic or flat. Next one is planar. Planar means sp2 or sp hybridized carbon atoms or heteroatoms are there. Then it must contain C2 axis. C2 axis means after rotating 180 degree, we get the equivalent structure. Then if number of pi bonds are even, it is non-aromatic. If number of pi bonds are odd, then it will be aromatic. Here is the example. Here bypassing C2, it is also non-benzoate because no benzene are there. It is cyclic, planar, that means all atoms here is sp2 hybridized. Then by passing C2 axis, we get the equivalent structure. So now count the number of pi bond 1, 2, 3, 4. Since here is 4 pi bond, so it is non-aromatic. Which is even? 4 is even, so it is non-aromatic. Next one is, it is also cyclic, planar because all carbon atoms here is sp2 hybridized. Then by passing C2 axis, we get the equivalent structure. Now count the number of pi bonds 1, 2, 3, 4, 5, 6. Since there is 6 pi bonds, which is ethene, so it is non-aromatic compound. Here the system is cyclic. All the carbon atoms are also planar because sp2 hybridized. Next, see the C2 axis. Here is also C2 axis is present. So next count the number of pi electron 1, 2, 3, 4, 5. 5 number of pi bond are there, which is odd. So the system is aromatic. Now for fused ring. For fused ring, there is a rule that for aromaticity we will count only the pi electron or pi bond present in the periphery. The pi bond present inside the ring or inside the system are called non-Hockel pi bond. They are not involved in counting aromaticity. So here 1, 2, 3, 4, 5, 6, 7 pi bond is present. System is cyclic, sp2 hybridized, planar. Also there is complete delocalization of pi electron. So the system is overly aromatic. Okay, then stability order, aromatic compound is the most stable. Next one is non-aromatic. The least stable is the anti-aromatic. Here is a set of question from previous year course of NET June 2011 and NET December 2014. So hope you all guys like this session and let me know the answer in the comment section. Thank you so much for watching.